Bismillahirrahmanirrahim. So I would like to present about introduction. This study examines the mathematical foundations of Google's PageRank algorithm, particularly emphasizing the significance of eigenvalues and eigenvectors in establishing web page rankings. The scope encompasses a true examination of the algorithm's dependence on the stochastic matrix structure of the web, the utilization of Markov chains, and the calculation of the primary eigenvector to designate relevance score to web page. Moreover, the research examines how this mathematical principle tackle issues related to ranking precision, scalability, and efficiency within large-scale web search systems. By grasping the mathematical basis of PageRank is essential not just for web search, but also for wider uses in network analysis, recommendation system, and social media analytics. The study emphasized the algorithm's capability to tackle the industry issue of ranking relevance within large dynamic datasets, an obstacle that keeps increasing with the growth of digital content. This paper offers valuable insights into how mathematical principle can be leveraged to address real-world issues by examining the PageRank algorithm through eigenvalues, establishing a basis for innovation in web search technologies, and more.
First, understanding the context. Explore using eigenvalue in the Google PageRank algorithms, which rank web pages based on their importance within a network. Second is formulating the problem represents the web as a directed graph where nodes are web pages, are edges, are hyperlinks. A stochastic metric defines the transitions probabilities between pages. For number 3, deriving the PageRank equation. Use the iterative formula, modify it to include a damping factor where is a metric ensuring is column stochastic. Solve the eigenvalue equation to find the steady state score. For number 4, solving the eigenvalue problems, we formulate as finding the principal eigenvector of corresponding to, simplifying to. For number 5 is numerical solution. Use the power iteration method. Start with an initial vector with positive values, interactively compute normalizing each after step until converges. For number 6, analysis and optimizations, study the sensitivity of score to the damping factor commonly, address issues like disconnected subgraph to ensure meaningful rankings.
We're going to talk about why eigenvalue and eigenvector are central. What is eigenvalue? Eigenvalue is the scalar such that applying the matrix to the vector scale the vector without changing its direction. Eigenvector is the vector that satisfies the above equation, represent the importance score of web page in a stable state. So in this part, there's like 3 categories, which the first one is data analysis. Eigenvalue and eigenvector can help reduce noise in data, improve efficiency, and eliminate correlated features. And the second one is computer science. Eigenvalue and eigenvector can be used in dimensionally reduction, graph theory, network analysis, and quantum computing. And the last one is engineering and science. Eigenvalue and eigenvector are used in many applications, including control theory, vibration analysis, electric circuit, advanced dynamic, and quantum mechanics. The second discussion is going to talk about how does Google use eigenvalues algorithm. There are also 3 categories or part, which the first one is PageRank algorithm. So the PageRank algorithm uses a transition matrix to represent the relationship between web pages. The matrix shows how likely someone is to go from one page to another by following links. Google then assigns each page an importance score called a PageRank vector, which is calculated by solving an eigenvector problem. So the second one is detecting link spamming. The second eigenvector of the Google metric can be used to detect link spamming. Link spamming is when links are placed between websites to increase their PageRank value. And the last one is computing the eigenvector. The power method is the only viable method for computing the eigenvector because of the Google metric large dimension. The last one is we're going to talk about why is Google PageRank an eigenvector problem. So the first point is PageRank in linear algebraic terms. PageRank creates a vector of rank, one element for each page. It also creates a matrix of links each link from one page to another puts a 1 in the appropriate cell of the matrix. Then it takes that vector initially set to some default and repeatedly applies the link matrix to it. And the last one is the power of eigenvector. Given the eigenvector and eigenvalue of a matrix, we can create 3 matrices that we can combine at the same way at the original, and the middle one handle all the scaling and it itself a diagonal matrix with the eigenvalue of the matrix as its entries. Exponentiating the original matrix is equivalent to exponentiating only the middle matrix of the diagonalized matrix to you. And exponentiating a diagonal matrix is equivalent to exponentiating only the entries on the diagonal.
So next, I want to present example of eigenvalue. So the first example is matrix A is a 5 by 5 matrix, where is the first row is 0 1 0 0 0, the second row is 1 0 0 0 0, the third row is 0 0 0 1 1 over 2, the first row is 0 0 1 0 1 over 2, the last row is 0 0 0 0 0. V1A in brackets is a two-dimensional subspace of eigenvalue corresponding to an eigenvalue of A. Vector X is equal to the transpose of the row vector 1 over 2 1 over 2 0 0 0, and vector Y is equal to the transpose of the row vector 0 0 1 over 2 1 over 2 0. Any linear combination of these two eigenvectors will also to V1 A in brackets. For example, the vector 3 over 4x plus 1 over 4y equals the transpose of the row vector 3 over 8 3 over 8 1 over 8 1 over 8 0 is another valid vector in the subspace. The total number of page is n, and the web is divide or R subweb W1, W2 until WR with NI page in subweb WI. So next explanation, for example, matrix A is block diagonal with its block AI representing the link matrix for subweb WI. Its block AI is a column stochastic matrix, meaning it has an eigenvector Vi with eigenvalue 1. For subweb WI, construct a vector WI that places Vi in the corresponding block and fills the other blocks with zeros. This meaning that WI, the eigenvector Vi for block AI and zeros for other block AJ, where J not equal I. It is easy to see the vector Wi 1 less than I less than R is a linearly independent eigenvectors for A with eigenvalue 1. Based on the picture, V1A has dimension at least R. Since there are R linearly independent eigenvectors W1, W2 until WR.
To conclude, this study addressed the issues of ranking web pages efficiently on a large scale and with mathematical rigor to satisfy the requirements of extensive web search. The research examined the significance of eigenvalues in Google's PageRank algorithm, highlighting how mathematical concepts support the algorithm's capacity to evaluate the importance of web pages according to their interrelationships within the web graph. The study also illustrated how the PageRank algorithm utilizes a stochastic transition matrix to represent the web as a Markov chain, with the main eigenvector denoting the steady-state probability distribution of web pages. This method offers an effective way to rank while also guarantee stability and relevance through the inclusion of damping factors to tackle real-world anomalies like dead ends and isolated subgraphs. Furthermore, the algorithm's mathematical framework allows for scalability, rendering it appropriate for managing the extensive and ever-expanding web.